happens at, this is a real thing, this is being put in community networks in a lot of parts of the world.
Yes, indeed. So I'm John, and I'm going to talk about LoRaWAN, which is a network, and the Things Network, which is an organization that offers the equivalent of a mobile network controller for LoRaWAN IoT networks. Slide, please. So what is LoRa? LoRa is a physical radio protocol designed for the Internet of Things. It operates in lower than 1 gigahertz ISM bands, so whatever happens to be free in your country. In this part of the world, it tends to be around 923 megahertz. In New Zealand, we have a band from 864 to 868. We also have a band from 915 to 930. I should say that I am staying in Singapore temporarily right now, but I live in New Zealand, and you can tell I'm from New Zealand because of my accent. Sorry, I'm actually from the States, but New Zealand's been home for a long time. So LoRa is a radio technology that's proprietary to a company called Semtech. And I know that kind of sucks that it's proprietary, but when you look at things like Wi-Fi, which is the foundation of community networks all over the place, there is proprietary intellectual property in Wi-Fi, and license fees get paid through and so on. So it's not all that different. So anyway, Kanchana's network, the TalkNet mesh, that's tens of megabits per second, and their backhaul is 200, so you're talking broadband. And this LoRaWAN stuff is like 250 bits per second to maybe 22 kilobits per second, but really the topologies and the applications that I've been working with over the past 4 years have been in the range of a kilobit per second or less. Next, please. So what is LoRaWAN? So LoRa is the radio protocol, and you don't need to use LoRaWAN to use LoRa. You can actually make a point-to-point connection with LoRa modems. Some people use them for controlling drones. Some people have used the LoRa protocol for other network types, but LoRaWAN is an open, non-proprietary standard for a wireless network. And it, as I said before, the whole thing with the mobile network controller, well, LoRaWAN adds addressing, mobility, and localization to LoRa. It adds this whole idea of you can have a network with lots of base stations, devices that move from one base station to the other, and everything just kind of holds together. So with LoRaWAN, it's pretty cool. Multiple base stations can receive and process packets. So like if this clicker were a LoRaWAN node, like out there in the network, he sent out a message. That message would be picked up by any base station that's in this room, and all of those base stations would relay the data to the mobile network controller, which would then say, hey, I've got a whole bunch of packets of information. These are the same ones. It does the deduplication. And then it decides when the network wants to talk to this little clicker, it decides, well, which of the base stations is closest to this clicker, and then routes the return message through the nearest base station. LoRaWAN also adds an adaptive data rate scheme so that devices that are near to base stations talk with a very complex modulation, so the message gets really fast. Devices that are really far from the base station talk with a really simple modulation, really, really slow, lots of airtime. LoRaWAN also adds multiple layers of encryption, network encryption, and application encryption. The cool thing about this, I say I've been working with LoRaWAN for 4 years. I've been a network operator, and I have no idea what the end users of the applications are doing, because all I see is encrypted packets and metadata going across my network. I don't know what's in the data, and I can't, because I don't have the keys to unlock that data. So LoRaWAN also supports time slot scheduling, noise transmission, and makes everything harmonious when you've got thousands of devices talking to a couple of base stations. Next, please. So the various entities in a LoRaWAN network are end devices, which is my clicker, gateways, which I don't know, we could call these massive chandeliers that come to gateways. Then in a lot of networks, the gateways use LTE or 3G backhaul, but they could use fiber backhaul, ADSL backhaul, whatever, to get into the network server. In the case of my network, the network server is an application that runs on AWS. In our case, we use AWS Sydney for New Zealand network. We use AWS in the Bay Area for our Cook Islands, for our Tonga network. And then there are applications, and applications could be separate from the network server, but in the case of most LoRaWAN controllers, applications are bits of code that sit inside of the same computer that's running the network server. Complicated. Next. So I'm going to give you a very quick LoRaWAN architecture overview, and this is based on RFC 8376. This is so appropriate for being at an IETF meeting. I'm just going to walk you through LoRaWAN based on the RFC that we're all writing our network software to. Next. So there's an end device, that's our clicker here, sometimes called a mode. It communicates with the gateways. It never talks to another mode, never talks to another end device. Everything is always through a gateway, through a network controller, to an application, and then from that application back down the chain to the end device. This guy has a unique, globally unique identifier called the device UI, and that's an IEEE number, and has a network unique identifier called the device address. It's a 32-bit address. We're talking sometimes about sending like 1 or 2 bytes of data, so when you start adding a 32-bit address or 64-bit address, you've got a lot of overhead there. Anyway, next. So our end devices. Here's an example of an end device. This is just an example. Next. You can look at the slides later. There are 3 classes of devices. The ones that are used most often are Class A. Communications is always initiated by the end device. It's a node, it's out there, it decides, hey, I've got a bit of data I want the rest of the world to know about. It sends the data, Aloha based. So it could be that data, I guess it doesn't get through the first time, whatever. Eventually it sends the data and it's acknowledged, and that's all good. After it sends the data, it listens to the network to see if the network wants to talk to it. So there's a time slot set up for the network to reply back and say, hey, I got your data, or hey, I got your data, now go to sleep for the next 6 months because I don't need you for then, or some other message. Now, Class A is lowest power. Class A is great for a battery-powered device that's out there in the environment doing environmental monitoring, needs to last forever. Class B, on the other hand, listens to the network on a schedule. Say maybe it wakes up once an hour and listens, wakes up once a day and listens, what have you. Very uncommon Class B devices. Most commercial implementations are either for Class A or for Class C. Now, Class C is just fine if you have solar power or electricity or just some massive source of energy, because it stays awake all the time, listening to the network to say, hey, does the network need me? Think about a farm, and you've got a whole bunch of Class A devices out there measuring soil moisture, and they're sending their data up. They're all battery powered, whatever, but then you've got a solenoid or a valve on the water system to add more water. That can't just be, asleep all the time. It needs to know, does the network want you to turn on and water the grass? So use a Class C for a control mechanism on the water. Next. So LoRaWAN gateway. It's a radio on the infrastructure side. These italicized are actually straight from the RFC. I've noted that I've actually lifted phrases straight out of the RFC to describe this. So sometimes gateways are called concentrators or base stations. I use base station and gateway like interchangeably. They communicate with end devices via the LoRaWAN protocol, and they communicate with the network server via TCP/IP. In the case of the base stations that I manage, they use WebSockets. In the case of the original implementation of the Things Network, there were UDP packets going from the gateways to the network server. So gateways, you can put a LoRaWAN gateway on a base station that's running other things like Bluetooth or Wi-Fi. I have Linux boxes that run LoRaWAN gateways, multiple instances on the same box, deal with multiple radios, and they might run other things, packet processing software or Wi-Fi or whatever. It's just a software application that interfaces with the radio. Next. So here's a few examples of LoRaWAN gateways. And yes, I've used all of these little boards and multi-text and things, networks, things, and whatever. Next. So a network server is a piece of software. It terminates the LoRaWAN MAC layer, even though there's some TCP/IP in between. For end devices connected to the network, it's the center of the star topology. We've got stars of gateways and stars of end devices. The network server decides what gateway is going to talk to what end device. And it's also going to tell the end device what data rate it should be transmitting at so that the gateway can best handle the amount of traffic and the amount of signal coming from close nodes and far nodes. So here's some examples of LoRaWAN network servers. The one I use in production is LoRaIoT, which is a Swiss company, but I use the Things Network for training workshops. And I've got a Things Network connected gateway in my apartment in Singapore now because I really love what they're doing and I really like the features of their network now. 4 years ago, it wasn't an option for doing real applications that you wanted to work, and today I think the Things Network is good for anything. Next. So a joint server. Okay, this is super complicated. Devices have sets of encryption keys going on. A joint server is what allows devices to get on the network. Go to the next. It's usually combined with the network server. An uplink message is when the node talks to the network. And yes, the uplink can be listened to by multiple gateways. Go on, next. Downlink message is when the network is talking to the node. And again, the network controller, the network server is what decides which gateway is going to send that message. It's also going to decide whether that message is going to go to a single end device or to a group of end devices. Next. Now, a LoRaWAN application is application layer code that's running on the end device, and it's application code running behind the network server, and there's a set of encryption keys tying these things together. Most end devices will only ever run one application. This is kind of how LoRaWAN has evolved. You have individual devices that do very limited, simple things, and they only talk to one application server. So applications typically run on network servers. Applications do device management, which devices are allowed to talk, what are they allowed to do. They route data to external applications, and that means they offer up an API that says, right, you can get data out of this LoRaWAN application via WebSockets, via MQTT, via JSON, via HTTP GETs, or what have you. So it is a misleading name. We could be calling these applications application routers. Next. Encryption. All the payloads are encrypted. So I said I'm a network operator. I have no idea what my end users are doing with the data. That's because the payloads are encrypted. I don't have the keys to open that. There's also data integrity. So there's sequence numbers that are encrypted that I don't know about, that the application owner knows about. So someone can't record a message and do a replay attack. Someone can't attempt to insert random messages in there because they'll be out of sequence and they'll be rejected. There's also data integrity because there's checksums along with the encryption. So you can't change the data in flight, you can't intercept, you can't replay, blah, blah, blah. MAC commands are protected. So nobody out there listening to the network can actually see any of the metadata associated with these transactions. In fact, if they're just listening without the network encryption keys, it's just noise. In fact, a lot of times it's noise below the noise floor. So it is really almost undetectable and impossible to see what's going on. Next, almost done. Right, pre-joined devices. You have ideas of devices that you join to the network once the end user has the device in hand, and you have the idea of devices where the manufacturer of the device joins it to the network ahead of time before they send it out in the field. And in this case, the device is pre-joined to the network. We put symmetric keys, 2 symmetric keys in the firmware of the device before we send it out to the field, a network session key and an application session key. These session keys they are session keys, so they can get rolled later, so they can get refreshed down the road, and frequently will get refreshed every time you rejoin the network, but this gets them on the network to start. Next. And there's the idea of an over-the-air join, where the network operator will send out a network session key and an application key, and the user will write those into the firmware, and then the device will send its device EUI, its app EUI, and its app key, and the network will basically derive app session keys and network session keys, those ones that if we did a pre-join, like in the last slide, the network and the device derives those things in a cryptographically secure manner so that these devices can talk. Right, next. So what is the Things Network? All of this complicated stuff to do with the network server, like, this isn't easy stuff. And I've never run my own network server, although I've downloaded the code and tried before. The Things Network is a free distributed network controller that a group out of the Netherlands put together so that people could have community LoRaWAN networks. They said, well, look, we're going to write a software implementation, we're going to make it all open source, we're going to have the community work on it, and we're going to let anybody who wants to connect to our network server spin up their own applications, generate their own keys, and join their own devices to these networks. So TTN, The Things Network, it provides a network server, join server, and application servers in one. We have a nice web interface, a web platform that allows application owners to register devices. I could use the Things Network if I just had a login to create an application and some devices, and I used someone else's gateway. In a lot of cities in this world, there are enough gateways that you don't need to run your own. Or you can be like me here in Singapore. I provide TTN gateway out of my apartment, but I don't actually have any applications running on it. I'm just running the gateway because I can, and I like the idea of it, and maybe I'll run an application at some point. All gateways on the Things Network process all traffic from all devices joined to the Things Network. So it is truly a communal thing. In Europe, they've got very strict restrictions on how much airtime your device can use so that an individual device can't take up too much network resources. So TTN provides all of this for free. They also help communities organize and communicate by giving them space on their website and allowing them to open up chat channels and post notices of meetups and so on, and linking their profiles. And so when I came to Singapore, I said, what's the TTN community in Singapore? I went and I found people's LinkedIn profiles on the TTN page. I sent them messages. I said, what's the story? What are we doing? When are our meetups and stuff? Same thing when I did a workshop in Santiago, Chile last year. I went to the TTN page. I found that they had a Telegram group. And the Chilean TTN community, LoRaWAN community, is just fantastic. There's like 30 people in the Telegram group. There's new posts all the time. And if I spoke Spanish instead of the case everything you translate, it would be really, really neat. So keeps the TTN all over the world. So where is the Things Network? Yeah, this is how many there are. There's more than 200 cities, and there's extensive coverage in some cities. It's pretty cool. I know University of Hawaii has just spun up a couple on my recommendation for some data collection things because they needed to do data collection and they wanted an open platform, so TTN. What else do we have? We must be almost done. Next. Here's a view of the console if you're logging in. That may be a bit small for anybody to see, but you can see my gateway there and some of the things I can control. In fact, there's a gateway ID. Here's the pointer. Yeah. This is gateway IDs and things. Next. So what does TTN integrate with? TTN provides these applications, and all the applications do is route data. So there are cloud applications you can use to talk to TTN, and some of those include KIND devices, open sensors, Mapper, Close. I have no IFIT. Some people in here will know what IFIT is. It's a platform that allows you to do things based on data. So in addition to these integrations, which are like super easy to set up, you can also just get JSON data or just get WebSockets data or whatever out of the controller. Next. I think we're in. That's it. So I've just got pictures of devices. Let's just scroll through that. Next one. With the last slide. All right, so that's it. So yeah, I guess any questions?
Anyone have a question for John? We have a minute.
I have a question for you. I saw your map. My question was about your map, like a few slides before. I see that you have some presence in North America. I've been part of a group who started looking at communication in northern Quebec, and so you have no dots there. Northern Quebec, by the way, is eastern coast, go up, and it's the big thing that right now there's no dots in it. And I was wondering if you guys have thought of your same type of communication in remote areas in Canada, which will never be served by any form of, broadband, traditional network, yet have an incredible need for communications and for access. So I was just wondering if you had plans in Canada. I see you have Alaska, which is cool, but nothing in my neighborhoods.
This is a group of communities, and so if your community wanted to start a LoRaWAN network, your entry cost for a gateway is less than $100. I think it's around $70 US. You can buy a gateway, and you need IP backhaul. Now, the amount of IP backhaul that you need to run this is in the kilobits per second. So any satellite connection would solve this problem.
Well, actually, one thing I wanted to, we can talk offline too, but that in these northern communities, they always have credit unions, and those credit unions have some form of connectivity, and we had thought of using them as hubs.
It's a very good idea to use this as hubs.
Thank you.
Okay, thank you. Let's give John a round of applause.